As a diver descends, the environment becomes increasingly hostile. You can feel the weight of the seas stacking up above you, pressing inward from every direction as the light fades. At the surface, the human body is accustomed to 1 atmosphere of pressure, but descend just 10 meters, and that pressure doubles. Every subsequent 10 meters adds another full atmosphere of force. Surviving at these depths requires vessels engineered to withstand thousands of tons of continuous force. A submarine's hull acts as a rigid bubble, resisting a physical assault that would instantly compromise a standard ship. Inside these hulls, the crew monitors that force through dials, where depth and pressure are displayed side by side. At these scales, the 2 metrics are essentially synonymous. To build these structures, physicists must move beyond simple measurements and isolate the 2 variables that dictate the crush: the density of the fluid and the total depth of the column. To understand the weight of an entire ocean, we have to ignore the scale of the sea and look at a single, stationary column of water. Imagine isolating a perfect cylinder of water and suspending it in a void. We define this element by its height, h, and its cross-sectional area, a. Since the fluid is at rest, the forces must be in perfect equilibrium. The downward pressure from above, plus the physical weight of the water, must be exactly balanced by the upward pressure pushing from the bottom. We can express this balance as an equation. The difference in pressure across the area of the cylinder is equal to the mass of that water multiplied by gravity. We know mass is simply density, represented here by the letter rho, multiplied by volume. And since volume is just height times area, we can substitute those variables into our force balance. When we look at the math, the variable for area appears on both sides of the calculation. It cancels out completely. If we move the top of our column to the surface of the water, the downward pressure becomes the weight of the atmosphere. We label this value P sub A. This provides the calculation for absolute pressure, the atmospheric weight at the surface, added to the product of density, gravity, and depth. The gauge pressure, the extra force applied by the water, depends strictly on how deep you go and how dense the fluid is. Mathematically, the shape or width of the container has no impact on the final result. This derivation leads to a conclusion that often defies intuition. The total volume of water surrounding an object has 0 effect on the pressure at the bottom. This is demonstrated by the hydrostatic paradox. Consider 3 glass vessels with wildly different shapes and volumes, all connected by a single pipe at their base. If you fill one vessel, the water doesn't pile up in the wider container. Instead, it rises to the exact same horizontal level in all 3, regardless of their capacity. The math confirms why. Because the density and the height of the liquid are the same in each vessel, the pressure at the base of each container is identical. The system is in balance. This vertical truth is the basis for instruments like the mercury barometer. For centuries, we have measured the weight of the entire atmosphere by simply tracking the height of a liquid column against a vertical scale. It means that if you are 10 meters deep in a narrow vertical pipe, you are under the same pressure as a diver 10 meters deep in the middle of the Pacific Ocean. While a massive body of water appears more threatening, the physics are clear. Pressure is not a product of volume, it is determined entirely by how much water is stacked directly above you.